We'll construct finite fields. Finite fields have prime characteristic p. That is to say, if we take p times the element in a finite field, we find 0. Moreover, finite fields have order p to the k, where p is prime, equal to the characteristic of the field, and k is a positive integer. So the first property we want to know is that a finite field of order p to the k exists and is unique. The second property is that we can characterize its elements as the roots of the polynomial x to the power p to the power k minus x. So all the elements of the finite field appear in this decomposition. And the third property is that we can also construct the finite field of order p to the k as a quotient ring, where the ring is a ring of polynomials with coefficients in the finite field of order p divided by a polynomial, where first of all it should be remarked that the finite field of order p is nothing but zp. That this is a field can, for instance, be proven fairly easily by using Bezout's identity. Moreover, so this is the coefficient field of the polynomials in X. And then what is the polynomial P? Big P is an irreducible polynomial in this field, in this ring. Of order K. All right. So let's look at the simplest non-trivial example of this construction. Let's take p equal 2 and k equal 2, and let's try to construct the field of order 4. So you might try Z4, but that is bound to fail because 2 times 2 is 0. So if 2 has an inverse, then 2 is equal to 0, and therefore this is not a field. But let's apply the construction above. We should think about roots of x to the 4 minus x, which is nothing but x to the x to the third minus 1, which is x times x minus 1 times x squared plus x plus 1. And this is nothing but x times x minus 1 times x minus a non-trivial root, third root of unity, and then x minus the square of that non-trivial root. So you can think of omega, for instance, as e to the 2 pi I over 3, and omega squared is e to the minus 2 pi I over 3, because e to the 2 pi I is 1. Or, well, okay, so we have the field of order 4. So it's basically generated by 1 omega, and omega square, and it has the fourth element, 0. So then clearly, for instance, omega inverse is omega square, etc. And one can easily check that this is indeed a field. Now, alternatively, we could have used the second property, which says that this is a quotient ring. So we need an irreducible polynomial of order 2, namely k, in polynomials over x with coefficients in Z2. Because remember, the coefficient field is GFP, which is GF2, which is Z2. All right, what is an irreducible polynomial of order 2? Let's try. We just put x squared. The overall factor doesn't matter. This is clearly reducible because x is a factor. If I add x, then x is still a factor. If I add 1, then this is irreducible, and in fact it's unique. Because, for instance, x squared plus 1 is equal to x squared minus 1, mod 2, and x squared minus 1 is reducible. So this is the unique irreducible polynomial in this case. And so we can have generators of the ring, which are basically 0, 1, x, and x squared, but x squared is equivalent to minus x minus 1, which is equivalent to x squared plus 1. So now we have a field with these 4 elements. And why is that equivalent to the field of elements with these elements? Well, we can identify x with omega, but then we should somehow identify x plus 1 with omega squared. Well, why is this the case? Well, x plus 1 is nothing but minus x squared if we divide by the ideal generated by x squared plus x plus 1. And therefore, mod 2, this is again equal to x squared. So indeed, if x is omega, then x plus 1 is equivalent to x squared. So again, this is the finite field of order 4. Now, for generic b to the k, there is no canonical construction. For instance, canonical choice of irreducible polynomial, but there is always a construction. Now, a further property is that we have a Frobenius, we have Frobenius automorphisms of fields, and they map each element to x to the p inside GF of p to the k. And in fact, the non-trivial automorphisms will be phi to the power 0, so the identity phi to the power 1, 2, etc., all the way up to phi to the power k minus 1. These are non-trivial automorphisms of the field. And they leave the subfield GF of P invariant. So these are Galois. This is a Galois group for the field extension GF P to the K of GFP. And the Galois group is formed by the automorphisms, which is Z to the k here, set k here. And so if we look at the example again, for the field of order 4, we have a Z2 group of automorphisms, which has one non-trivial element, which maps omega to omega square, vice versa. And therefore, it's equivalent to mapping I to minus I, much as in our discussion of Galois theory and complex numbers.